Welcome to my second video on vehicle electrical systems. This video is on circuit basics as far as types of circuits, faults in a circuit, and circuit calculations. To start off, we can see the reoccurrence of the voltage triangle. I talked about it originally in the first video. Uh, just a brief summary of it again. Voltage, which is at the top of the triangle, is equal to current times resistance. So current and resistance are directly proportionate to one another. As current goes up, resistance goes down. As resistance goes up, current goes down. Now, introducing something new, we have the power triangle. It's the same format as the voltage triangle or Ohm's law triangle, depending on what you want to call it, with P at the top standing for power. Power is measured in watts. You can see current and voltage are at the bottom. Calculating for wattage, you have power equals current times voltage, which is the same thing as the voltage triangle, which is voltage equals current times resistance. Same format, calculating something different. Now I want to discuss some Kirchhoff laws. First law up is Kirchhoff's current law, which states that the sum of currents flowing into a node is equal to the sum of currents flowing out of that node. What that's saying is, let's say we have this circuit here. There's a 12-volt battery source at 10 amps. Well, at this node here, this connection point right here, we have 10 amps flowing in. We can't have more than 10 amps flowing out. What we actually have between them is a split of that 10 amp. It's not going to evenly split unless if the resistance of each side of the circuit is the same. So it'll split exactly 10 amps worth of current based off of the resistance in each circuit. So in the bottom circuit here, we have one resistor, which allows 6 amps of current flow, and this resistor, which allows 4 amps of current flow. And then when they reach back to this junction or this node, they combine and have an output of 10 amps. The input amperage is the same as the output amperage. No amperage is lost in a circuit. Now let's talk about Kirchhoff's voltage law. Kirchhoff's voltage law states the directed sum of potential differences around any closed loop is zero, which is basically the sum of all voltage drops is equal to the source voltage. Let's talk about voltage drops. For voltage drops, obviously in a whole circuit, we've talked about it. With one consumer, we'd have a voltage drop of 12 volts. Now, if we have multiple consumers in one circuit, we can't have 12 volts dropped across all of them because after the first consumer, we would have no voltage left. So it gets split among the consumers. How it's divided among the consumers is based off of the resistance of the consumer. Now, the example I have here, I have 3 different resistors. Each, let's pretend they're all light bulbs, and each have their own voltage drop across. This one would be the highest resistance consumer, or the highest resistance light bulb. The biggest voltage drop would be across this light bulb. The second biggest voltage drop would be across this light bulb. And the third biggest voltage drop would be across this light bulb. Keep in mind, all the voltage drop across all 3 light bulbs is equal to 12 volts. And if you knew the amperage on the circuit, you could also figure out the resistance of each consumer. Let's say the amperage on this circuit is 4 amps. If the amperage is 4 amps and the voltage is 12, we have a total circuit resistance of 3 ohms. To calculate each resistor's resistance, you would take the voltage drop across the resistor, for example, 6 volts, divided by the amperage, 4 amps in that circuit, would give us 1.5 ohms. And if we take 4 volts divided by 4 amperes, it would give us 1 ohm. And if we had 2 volts divided by 4 amps, it would give us um, 0.5 ohms. If we were to add all these up, we would have a total 1.5 plus 1 is 2.5 plus 0.5 would be 3 ohms, which is our total circuit resistance we already calculated. Now I want to get into types of circuits, and starting off, I'm going to start off with series circuit, which I already introduced a little bit earlier with the series resistors for calculating voltage drops. In the series circuit, this is a basic circuit that we have here. We have a 12-volt battery. Keep in mind the battery symbol. The small post is always the negative, and the long post is always the positive. You also see these symbols here. These symbols are just symbols for ground. And what that means is basically there's an invisible wire that goes all the way along here and connects that circuit back up. It makes it easier for when you're drawing wiring diagrams that you can just draw it as a ground symbol, because sometimes you're grounding it to a frame, sometimes you're grounding it to a grounding block, and it's just an easier way of drawing a ground which might not have a specified ground wire going all the way back. Now, with this 12-volt source of a battery we also have a 4 ohm resistor. Now, if we have a 4 ohm resistor and a 12-volt source, how much amperage do we have? Well, we take 12 divided by 4, give us 3. Give us 3 amps. And I want to talk about real quick, how would higher resistance affect the main consumer in a series circuit? Let's say this 2 ohm resistor, this is our light bulb, right? And let's say this 4 ohm resistor is corrosion within the wire. That light bulb is supposed to have the voltage drop across the circuit. That light bulb is supposed to see that 12-volt drop. But if we have unwanted resistance in this circuit, this 4 ohms of unwanted resistance, we're not getting that 12-volt drop across that light bulb. It's rated for 12 volts, but it's not getting 12 volts. How much voltage is it actually receiving? Or how much voltage is actually being dropped across that light bulb? Let's calculate it real quick. Now, to calculate total ohms of resistance across a series circuit, you just add them. So we have 2 ohms here and 4 ohms here. If you add 2 ohms and 4 ohms, we get 6 ohms of resistance. To calculate the amperage, we can take that 12 volts divided by 6 ohms, and we would get 2 amps of current. To calculate the amount of voltage being dropped across each resistor, all we have to do is take 2 amps of current, multiply it by the 2 ohms that we see there, and we know that our first voltage consumer, the light bulb, is only receiving a total of 4 volts. That's very low, which would mean that our 4 ohm resistor, multiplied by the 2 amps, is receiving 8 volts. If we add 8 and 4 together, we have 12 volts. That's our total consumer. We always have a 12-volt circuit drop across the entire circuit, and our light bulb will not work. Now, getting into types of faults in a circuit, besides this higher resistance, we have many other types of faults. Our first one here being an open. With an open, we have 12 volts that end right at the end of the open. This is an open wire. These two are not connecting. You're not going to have any voltage that comes this way. whatsoever. You're going to have 12 volts that ends right here, and that 12 volts is going to sit there, and there's going to be no flow whatsoever through that open. Let's look at the one right below it. You can see that this is another open. That wire is open there. Is there going to be voltage over here? And what's the voltage going to be there? We obviously have a resistor here. Is that going to change the voltage that's supplied to the very end of the wire? No, it's not going to change anything. Because it's an open, we have no flow. Therefore, we're going to see source voltage at the last point of that wire. This is important when testing equipment because a lot of people, when they're testing wires, they'll take their multimeter and they'll check that wire right there. They'll see 12 volts and they're like, okay, that wire must be good. We got a 12-volt battery source. We see 12 volts right at that wire. But what they did was they unplugged the connector and they're checking the voltage at the connector without it actually being a full circuit. That 12 volts means absolutely nothing. That's why when you're checking circuits like that, to actually check the power going through that wire, you need a load. And a lot of times, the best way to put on a load, the best way to do it is hooking up a light bulb. We can hook up one lead there, hook up another lead there. If that light bulb turns on, you know that wire is good. But still, no current's going to flow through that open. Next one we have is a short. I already explained how this is a ground symbol. And if we did not have any sort of circuit protection device, this would be catastrophic. These wires would be burning, and you have a high risk of a fire potential because we have 12 volts going straight to a ground, which means our voltage drop of 12 volts is going to have to be through the small amount of resistance within this wire, which is going to allow high amounts of amperage through that wire, which is going to generate lots of heat. That is not good. That's why a lot of times to protect devices like this, we'd install what's called a circuit protection device. I'll get into circuit protection devices later. Examples of circuit protection devices are fuses, relays, circuit breakers. So if we had this drawing here, let's erase this real quick. What's the voltage going to be over here? Well, what you're going to see is because this wire is still connected to your source wire, you're still going to see 12 volts there. What voltage would you expect to see there across this consumer? Well, you would see 0 volts. It would still be a normal voltage drop, but I'm just going to say because it splits off like this, technically this here is no longer a series circuit. Originally it was a series circuit. With this ground here, it's no longer a series circuit. So what's going to change is the amperage, which I will explain later. In this circuit here, we have our 12-volt battery source, and we have a ground on the opposite side of our resistor. Is this going to affect your circuit at all? No, this is not going to affect our circuit at all. We have a ground here already. We have a ground here already. This is not going to change anything with our circuit. Our circuit's going to act normal. There's not going to be any change in the way our circuit functions. It's not wanted that it's grounded through here, but it does not damage or change our circuit at all. Unfortunately, I'm running out of time for this video, so I'm gonna just say I'm gonna make a part 2 of the video 2 for vehicle electrical systems, and I'm gonna cover parallel circuits and series parallel circuits as well. Thank you for watching the video.